Final piece we want to talk about is how do we prove independence. We've talked about independent events and dependent events, conditional probability, all these things. So we've kind of danced around this a little bit, but let's get a formal definition for independent events. We'd say that A and B are independent if the occurrence of each one of them does not affect the probability that the other occurs. So what that means, now that we've seen this conditional probability notation, that means that the probability of A given B is also equal to the probability of A given not B. And really what this means is that whatever B is doesn't impact A, since it can happen one way or the other. And that should just end up equaling what the probability of A is. So let me give you for instance, so you see what I mean. If I flip two coins, and rather than write heads and tails, I just wrote this as heads and not heads. If I call this event event B, and I call this event event A, if I want to find the probability of getting a head given a head, that is the same exact probability of getting a head given a not head. So no matter what, this probability here is 1 out of 2 for this coin flip, which is just the same as this coin flip getting a head is 1 out of 2. Doesn't matter what happened before this, I'm still going to have the same probability for this individual event, which is equal to the probability of A. So we can prove this, and we could say that using the rule that we saw before, that the probability of A intersected with B is equal to the probability of A given B times B. We see that these two things are independent if, and only if, the probability of A intersected with B equals the probability of A times the probability of B. So what that means is I can trace a path on this branch, and this is kind of what we've done before. The probability of both of these things occurring, that would be this, is given by multiplying this times the probability of this event and the probability of this event. So we kind of already know this. Here is just a formal definition. One thing to note is that this double arrow actually is pretty important. It means if and only if. Oops, there's just one if and only if. So it just doesn't mean, and it's a little bit more significant than if, because it means that I can prove this, or I can use this argument in both directions. If I'm given that two events are independent, then this must be true. Similarly, I can go the other way. If I'm given that this is true of two events, then they must be independent. So let's take a look at what an example of this is. So here I've got two different probabilities. The probability of event A occurring is 1/2, the probability of event B occurring is 1/3, and the probability of A or B is P. Let's find what the probability of P is if A, they're mutually exclusive, and B, if they're independent. So these are obviously two different scenarios. So if they're mutually exclusive, remember that means that I'm going to have two circles that do not intersect in my Venn diagram. So if I were to attack this one, what do I know about mutually exclusive events? I know that the intersection of A and B is equal to the empty set, or the null set. So what I can say is that the probability of A and B is equal to 0. And I know that the probability of A or B is equal to the probability of A plus the probability of B. And typically I would have to subtract that probability of A and B. You can look back at what we said before with that addition property, but if we're talking about mutually exclusive events, this is all that I need. I don't need to subtract 0 off of this. So that means that P, which is the probability of A or B, that's this, is given as 1/2 plus 1/3. So if I add these two things together, the probability of all this is going to equal 5/6. So if we're talking about mutually exclusive events, P, meaning A or B, has a probability of 5/6. If I were to talk about independent events, then I have to use a little bit different probability laws. If they're independent, then I have the probability of A and B is given as the probability of A times probability of A times the probability of B. This is what we just saw in the previous slide. So I can multiply the probabilities of these two independent events, and to get the sum of those probabilities. Why is that helpful? Well, I can find the probability of A and B to equal 1/2 times 1/3, which is equal to 1/6. And this is helpful to me because I can use that probability addition law. So I could say that the probability of A united with B is going to equal the probability of A plus the probability of B minus the probability of the intersection of A and B. So now that I know what all three of these things are, this is going to equal, this is my P from the given prompt, and that's going to equal 1/2 plus 1/3 minus 1/6. And I already know that 1/2 plus 1/3 is equal to 5/6. So 5/6 minus 1/6 is 4/6, which is equal to, oops, I already jumped ahead in my brain, which is equal to 2/3. And that is what P will equal if we're talking about independent events. So why don't you give this problem a shot? There's lots of parts to it, so lots to dig into. I'm giving you a couple probabilities, I'm telling you that these are independent events. Now find the probabilities of all of these A through E. So pause the video, dig into this one, give it a shot. And here are the solutions for each of these parts of this problem. So hopefully you were able to get there using those probability laws that we talked about.